Hello, my name is Joshua Taylor, and this is my lab report for Lab 3. Here's the table of contents. The purpose of this lab is to measure the distance dependence of the magnetic field due to a small bar magnet and compare these results to the computationally predicted results using equations derived from the Biot-Savart law. The models used to do so are both physical with a bar magnet and magnetometer, as well as a computational model using GlowScript. The physical experiment determines that the distance dependence power, n, is 2.752, and the magnetic moment of the bar magnet, mu, is 4.191. So here's the Biot-Savart law, which describes the magnetic field generated by a moving charge. And then this is the equation for the magnetic field generated by a dipole. Notice how its dependence on distance is related to a power of 3. The distance dependence can also be written as k, which is a constant, r to the n should be that power 3, and we can linearize this equation so that whenever we plot data, n becomes the slope of the graph. And then the dipole magnetic field at some distance can also be written as this equation, which will be used in the code later. The physical model uses a bar magnet, which is going to be the system, and it also uses a magnetometer app and other necessary items such as meter sticks. These items and anything else is considered to be the surroundings. The computational model of the experiment uses GlowScript, and this is all modeling a bar magnet and its field, which is a dipole, and that field looks like this image. So for the experiment, we use the magnetometer app to find the Earth's magnetic north. We locate the phone's magnetometer chip, which we do in part 1 of these images. We record the distance the phone is away from the magnet when it reads various magnetic X readings. From the generated plot of the data collected, we determine n and mu, and we observe the magnetic field at a 45-degree angle from the magnet. And here is how you observe it at a 45-degree angle in part 2. The data we collected is in yellow, and it generated this plot of linearized data from one of the equations previously stated. From this plot, we got the slope, which is the n value, to be 2.7522, which is very close to 3. And by using other given equations, we found mu to be 4.191. And it's important to note that we assume that the only magnetic fields at work during the experiment are from the bar magnet and from the Earth. So some experimental sources of error would be that nearby electrical equipment, steel or iron, created additional magnetic fields that were not accounted for. There are also some other possible sources of error given here. For the code, we used the Lab 3 starter code and put in the initial condition of the magnetic moment that we found earlier. We produce a function that finds the magnetic field due to this dipole at a given location. And then we choose 6 locations to observe this magnetic field from and model the field using arrows generated down here. So running this program, we see the bar magnet in the middle, and we see in blue perpendicular observations of the magnetic field. In orange are parallel or on-axis observations of the magnetic field. And in magenta, at the top, you can barely see that 45-degree angle magnetic field measurement. So the bar magnetic field was stronger computationally than experimentally. We know this because at R20 distance from the physical experiment, the X field was 27 microteslas, not 20. And at R220, it was 356, not 220. This is due to the experimental sources of error stated earlier. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the X direction, and as the magnetometer moves closer to the magnet, the measured X component of the magnetic field increases. Now here are the what-if questions and answers. For the first one, the results would have been inflated by the Earth's magnetic field readings just as they were in the Y component when measuring from a distance d away. And for the second one, if the magnet's poles were oriented in the same way, the measured magnetic field values would roughly double, while if the magnet's poles were oriented opposite of each other, the field should roughly cancel out. In conclusion, measuring a particular magnet's magnetic field can be very difficult because of the amount of magnetic forces being generated from the world around us. This is displayed in the discrepancies between the experimental and computational field strengths at different locations, but when outside sources are eliminated, the magnetic equations we have are very powerful in determining a field or magnetic moment. Thank you.